So in this video, we're going to talk about advanced control statements. So we briefly touched on counting in a loop before. A counter loop requires a control variable or loop counter. The control variable's initial value, some sort of increment needs to be applied each time to the loop, and the loop condition should see if looping should continue. So, for example, the program below shows that using a control variable, we declare it to be an unsigned int, reserve space for it in memory, and sets it to an initial value of 1. Declarations that require initializations are called executable statements. A declaration that also reserves memory is called a definition. So here's our basic example of a counter loop. So we started at 1, while counter is less than 10, print it out, and add 1 to it. And this should be count, not counter. Okay, there's a shorter way to do it called a for statement. The for statement specifies counter loop details in a single line of code. Initialization occurs once when the loop is encountered. The condition is tested each time through the body. The body completes, the body executes as if the condition is complete, and the increment occurs after the body executes. Then the condition is tested again. And here's the general format. We'll go over here and do a simple example. We'll say, first let's have our using, and then we will say for int counter, and we're going to start it at 1. You can either say equals 1, or you could go like this instead. I prefer this form, equals 1, and then we put our loop condition. That's counter is less than or equal to 10, count, and then our increment counter plus plus. And then we're going to say count, counter, and we will run it. Now, this is exactly equal to this type of thing. We could say int counter 2 equals 1, while counter 2 is less than or equal to 10. Statements. And run it. And it gives exactly the same results. Basically, these are synonyms for each other. One is just a little more compact. Okay. So here's the basic breakdown. We've got the for keyword. We've got our control variable name, the initial value of the control variable, our required semicolon separator, our loop continuation condition, and an increment of the control variable. So the general format of the statement is initialization, condition, and increment. Initialization initializes the loop's control variable, condition determines if the loop should continue exiting, and increment increments the control variable. Usually the for statement can be represented by an equivalent while statement. We show. If the initialization expression declares the control variable can be used only in the body of the loop. But if it's declared outside, you can use it elsewhere as well. Basically, the restricting of the variable within the block is called scope. The scope of a variable specifies where it can be used. So, in the for loop, the 3 expressions in the for statement are optional, but the 2 semicolons are required. If condition is omitted, C++ assumes that the condition is true, creating an infinite loop. If you omit the initialization, if the program initialized it earlier, you don't need it. And you could omit the increment expression if the increment is done in the body or of the for, or no increment is needed. there are opportunities for infinite loops there. The increment expression in the for statement acts like a standalone statement at the end of the body. The expressions counter equals counter plus 1, counter plus equals 1, etc. are all equivalent in the increment expression. The initialization, loop condition, and increment can contain arithmetic expressions. The increment can be negative, making it go backwards. If the loop condition is initially false, the body's not performed. Here's the UML. So here's some simple examples. To count from 1 to 100 by 1, we use this loop. To count down by 1, we use this loop. To go by increments of 7, we start at 7 and do the addition of 7. From minus 2, we do the same thing. To iterate over the sequence 2, 5, 8, 11, 14, 17. We would increment by 3, etc. We can use int or unsigned, depending on, to determine if the value is negative. You do have to be careful when going with negative values because you could end up with an infinite loop. So another example, so let's take this example of summing unsigned integers. The numbers from 2 to 20. So cut this out. Okay. And now we're going to go sum even integers from 2 to 20. And we'll print out the total. If we run it, it will show us the sum of 110. Okay, so now the do while statement is similar to the do statement, the while statement, except the condition tests after the loop, so it executes at least once. So, comparing and contrasting, if we use, if we use a do while statement, so if we say x equals 1 and while, x is greater than 0, actually, well, x is less than 5, and here we set x equal to 5, it's never going to run this loop, right? Or it'll run the loop infinitely, sorry. Less than 5, I'm sorry. It never does anything. But if we change this to be a while loop, or a do while loop, it would do this. And now if we run it, it prints 5 once because it guarantees we go through it at least once. You can convert between the two by creating a while loop with the insides occurring once before the loop starts. Switch performs a different action based on the possible values of a variable expression. Each action is associated with the value of an integral constant expression, and it's like a superpowered if based on constants. So what we could do is, using a switch statement to count letter grades, we could say enter the integer grades in the range 0 to 100, and then we could, for each grade, we're going to do a switch on grade divided by 10, just get the tens part. And if it's 9 or 10, we add to an A. If it's an 8, we add to a B, etc. The break here says stop executing these checks and go back to the top of the loop, the switch. Okay. If the first part of the program prompts the user to enter integer grades or type the end of file indicator. The end of file indicator is a system-dependent key press, either Control Z or Control D, usually. The switch statement consists of a series of case labels and an optional default case when everything else doesn't match. When the flow of control reaches the switch, the program evaluates the expression in parentheses and compares the expression to each case label. If a match occurs, statements for that case execute. The break statement causes program control to go to the first statement after the switch. Listing cases with no statement between them will execute the same set of statements for each case. Each case can have multiple statements. It doesn't require braces, but you should use them anyway. Without the break statement, each time a match occurs in the switch statement, it falls through to the next case until a break statement is found. So, if no match occurs between the expression's value and a case label, the default case executes. If no match occurs in the switch statement that does not contain a default, program just continues. Okay. So, you might have noticed this break statement. In addition to selection and iteration, C++ provides statements break and continue to alter the flow of control. The break statement, while in a loop or a switch statement, immediately exits that entire statement. The continue just exits that iteration. So, here's an example of using that. Okay, so here we're going to say, so we'll say for int I equals 0, I is less than 10, I plus plus, and then we're going to print out everything except number 5. So we're going to say if I doesn't equal 5, or if I equals 5, continue, and then we're going to count I equals oops. Okay, so now if we run this, what it'll do is, except for 5, it'll print the value. When we hit 5, we're going to hit continue, which will take us to the end of the loop and right back through it. So, 0, 1, 2, 3, 4, and we skipped 5. Now, the break statement kicks us out of the loop entirely. So, for example, this time, we want to stop if we hit 5, make it break, and it breaks us out of the structure. So this time when we run it, oops. Oh, I forgot. Break it. It goes 1, 0, 1, 2, 3, 4, and it hits the brake, and it exits the loop entirely. So the continue statement, when executing the loop, continue skips the remaining statement in the body of the statement for that iteration only. In while and do statements, the loop continues evaluation immediately after the continue statement executes. In the for statement, the increment expression executes, then the loop test evaluates. So here's an example. Break if the count is 5, just like I showed before. Okay, now, when dealing with ifs and whiles, C++ has logical operators used to form more complex conditions by combining simple conditions. They are AND, which is 2 ampersands, OR, and NOT, also called logical negation. The AND operand is true when two conditions are both true. The condition to the left of the AND evaluates first, and if necessary, the simple condition to the right of the AND executes next. So this is actually what's called short circuit evaluation. It stops evaluating as soon as it knows whether it's true or false. So in C++, false and false produces one and of false and false is false, and of false and true is false, and of true and false is false, and of true and true is true. The OR operator is true when either condition is true, and it starts evaluating from the left. Again, this time it's false and false is false, and every other operation is true. An expression containing AND and OR operations evaluates only until the truth or false of the expression is known, and this is called short-circuiting. NOT reverses the meaning of a condition. So it's a unary operator, and NOT of false is true, and NOT of true is false. So the example attached here demonstrates by printing out the various truth tables. Oops. Here, for example, we say logical and is false and false, and then false and false should be false, false and true should be true, etc. And it will produce a complete truth table. Now, using this, you now have a complete ability to do more flexible conditions. So, for example, we can now say x equals 3 and y equals 5. We can say if x equal 3 and y equal 6, count matched. Okay, in this case that'll fail. But if we change this now to say or instead, then it will work because one of the first one is true. So we'll just get one. All right. And this gives us the ability to chain multiple conditions. So if x equals 3 or y equals 5 and y equals 6, and x equals 2. Notice we just chained two conditions here, and by using parentheses we show the precedence, although technically speaking AND has prior precedence than OR. Okay. So, given that, there's one thing we do need to keep in mind, and that is people usually confuse equal and equal. It's a common mistake. It's hard to catch because this technically isn't a syntax error. But it can generate incorrect results that are hard to debug. Some compilers issue warn when equal is used where double equal is expected, but it's not guaranteed. This is because, and the reason it's such a problem is any expression that produces a value can be used in a condition as long as the value is 0 or non-zero. Non-zero value is interpreted as true. Variable names are called L values, left values, because they're used on the left side. Constants are R values because they're used on the right side. L values can also be used as R values, but R values can't be used as L values. For example, you can't assign 3 equal to A. That won't work. So this could give you a basic idea of how the different types of iteration statements work and the switch statement. And hopefully you can use these to structure the flow of your program in a efficient and useful manner.